welcome to this explainer. Today, we're diving into something truly fascinating from our source material. We're going to walk through exactly how to establish a secure, totally off-grid tactical data unit. Specifically, we'll be breaking down ad-hoc video link and ATAK integration over a standalone MANET. That's a mobile ad-hoc network. If you've ever wondered how to keep secure, high-definition data flowing when traditional infrastructure is literally non-existent, well, you're in the right place. Let's get into it. Picture this scenario. You're out in the field. There are absolutely no cell towers, zero internet connection. But your team desperately needs to maintain situational awareness, share live video feeds, and track movements in real time. So how in the world do you route high-definition video and highly sensitive telemetry over an autonomous software-defined radio mesh when the grid goes completely dark? That is the exact operational challenge we're solving today. Here is our mission outline for today. 1. The tactical off-grid objective. 2. Hardware and prerequisites loadout. 3. Board logic and kernel. 4. Linux network bridging setup. 5. ATAK and Jami configuration. And finally, 6. Field testing and deployment. Section 1. The tactical off-grid objective. Establishing the architecture. So what's our main goal here? Essentially, we are trying to bridge everyday commercial devices, like your standard smartphone, with custom mesh networking hardware. We're building an invisible data web. Just to make sure we're all on the exact same page, a MANET is that invisible, localized radio frequency network that replaces our missing cellular grid. It's totally autonomous, it's self-forming, and by utilizing a Zynq-7020 paired with an AD9363 Software-Defined Radio board, we're creating a tactical data unit, or TDU. This hardware becomes your backbone, routing decentralized video and data directly node to node. No central server required. Section 2. Hardware and prerequisites loadout. Physical asset inventory. You know what's wild about this loadout? It's surprisingly simple given the incredibly capable architecture we're building. For the physical rig, you need that Zynq-7020 SDR board running embedded Linux, something like Tezuka OS. Grab a standard Android smartphone to act as your end-user device, then you just physically tether the phone directly to the board using a USB-C Gigabit Ethernet adapter and an RJ45 cable. Throw in a high-density power bank, like a LiFePO4, and your physical setup is done. That direct Ethernet connection is absolutely crucial because it sets the stage for a lightweight internal daemons like DNS mask to step in and automatically assign IP addresses right there on the device. Section 3. Board logic and kernel. Preparing the embedded Linux core. All right, physically plugging things in is just step 1. To actually make this tactical data flow, the embedded Linux kernel on your Zynq board needs some very specific parameters enabled. If your firmware is missing these, you're going to have to recompile your kernel. You've got your standard requirements, Ethernet bridging, USB network drivers, but there's one you absolutely cannot ignore, config-ip-multicast. This is a total deal breaker. ATAK relies entirely on multicast traffic to broadcast telemetry to all nodes simultaneously. We also need essential modules loaded up, primarily the Batman-adv module, which acts as our Layer 2 mesh routing protocol. Now I want you to burn this number into your memory. 1460. Why does 1460 matter so much? Because we have to drop our maximum transmission unit, our MTU, from the standard 1500 bytes down to exactly 1460. See, RF mesh links add their own header baggage to the data you send. The Batman-adv protocol and the RF daemon both tack on extra bytes. If you leave your MTU at 1500, those packets get too bloated and the system is forced to shatter them into smaller pieces. That's called fragmentation. And for live HD TCP video streams, massive fragmentation means massive lag. By setting the MTU to 1460 bytes on both your TAP0 and ETH0 interfaces, you make room for that overhead and guarantee smooth transmission. Section 4. Linux network bridging setup, unifying the network layers. Okay, kernel is ready. MTU is optimized. Now we need to fuse our physical connections with those invisible radio frequencies. Think of ETH0 as your physical, hardwired connection coming from your Android phone into the SDR board. Then you have BAT0 and TAP0. That is your invisible, software-defined RF mesh layer autonomously talking to other nodes out there on the battlefield. Our goal here is to create a software bridge between these two distinct interfaces. We don't just want the phone talking to the board, we want it to become a fully integrated node on the entire mesh subnet. To build that bridge, you'll execute this exact 4-step sequence directly on the Zynq-7020 node. First, load the essential modules with ModProbe. Second, initialize the mesh by bringing TAP0 and BAT0 online. Third, create a local bridge interface. We'll call it BR0, and assign both your physical ETH0 and your mesh BAT0 as masters to it. Finally, bind a static IP address, like 192.168.50.1, to that bridge and launch your DNS mask service. Boom! Your command line configuration just transformed a standard radio into an automated gateway that feeds IP addresses to any connected phone.
Section 5. ATAK and Jami configuration, deploying the software stack.
The network is alive, data is bridging, so let's get our software talking. We're leaning on two main apps for this, Jami for video and chat, and ATAK for tactical mapping. Jami is incredible for this use case because it uses a zero-server peer-to-peer mode via localized IP discovery. You are completely bypassing the need for a central registry. Pro tip, though, dial your video codec back to 720p at around 15 to 20 frames per second. That is a critical adjustment to save precious RF bandwidth. ATAK, meanwhile, relies on Multicast UDP for its cursor-on-target tracking protocol. You'll set that up using a very specific IP address, 239.255.255.252. And when you're punching in that multicast address for ATAK, don't forget port 4242. That port is the exact gateway required for all nodes on the mesh to actually see each other's tactical telemetry. Oh, and there is one more absolute lifesaver hiding in those ATAK settings, your multicast time to live, or TTL. You have got to set this to 4 or higher. In the networking world, TTL determines how many hops a packet can survive between nodes before it's thrown away. Setting it to 4 or greater guarantees your ATAK data packets can physically traverse multiple hops across that Batman-adv mesh network without dying off before they reach your squad. Section 6. Field testing and deployment. Validating the network. All right, hardware and software are configured, but before you step into a total comms black hole, you have to run through these deployment validation checks. First, run the iPerf3 utility over your RF link. That gets you a baseline bandwidth throughput. Next, kick off a direct Jami P2P video call to appear on your 192.168.50 subnet to verify stream stability and make sure packet loss over the AD9363 channel is minimal. Finally, drop a few positional markers in ATAK. You need to confirm that those cursor-on-target placements replicate instantly with low latency across all connected Android devices on the mesh. Think about what we've just done here. We've literally taken off-the-shelf smartphones paired with standard software-defined radios and engineered a fully self-sufficient, high-definition comms array. No cell towers, no ISPs, no centralized servers. Which leaves us with a pretty profound question regarding the future of autonomous networking. How does true decentralization change our operational capabilities when the grid goes completely dark? Keep that in mind as you explore these off-grid architectures. Thank you so much for joining me for this explainer, and I can't wait to dive into our next topic with you soon.